Thanks very much for having me. I love being part of these WoodSolutions seminars, and yeah, I'm really honoured to be on here because I love the work that you all do. So today we'll be covering the pathway to net zero carbon, and we'll be looking specifically at timber and the role of passive house and those two together. So I'll just go through a quick introduction, which has kind of already been done, an overview of the passive house standard, a case study of what it would take to take a building from code to passive house, and then the opportunities of combining passive house with timber construction. And lastly, a local and international set of precedents. So hello, I don't need to dwell on this one because you've already introduced me, Alistair, thank you. But essentially I was an architect and now I work with architects to help them achieve their sustainability aspirations on their projects. And it's a really fun and rewarding role. So what we do at Atelier 10, just quickly, is quite broad. We work from anything from sustainability strategy all the way down to the nitty-gritty facade optimization, and yeah, everything in between really. So covering water systems, lighting design, carbon emissions, energy, everything. So our goal is to create really healthy buildings for people and the planet. As Alistair mentioned, I'm also a director at the Australian Passive House Association. So again, the overarching goal of this association is for all Australians to live and work in healthy, comfortable, low energy, resilient buildings. Live and work, sorry, not just live. So yes, that's, I guess, it speaks to my values as well. So the big picture. Now we've all seen these graphs before, so I won't dwell on them. But essentially we need to get to zero carbon by 2050, otherwise we're looking at some pretty serious consequences. So how do we do that? I think we have the tools, we have the ability, we just need to put it into practice now. So carbon emissions obviously are contributed to by buildings. 39% of carbon emissions come from buildings, with 28% being operational and 11% being embodied. Now that's not to say that embodied carbon is less important than operational, it just at the moment has a smaller chunk. That may change though. So the role of buildings, we really need to look at our upfront carbon. As I say, the 11% of emissions really does take a big chunk at the beginning of a project stage. So looking at the materials we use and replacing very carbon intensive materials such as concrete and steel with timber would be a really great outcome. Obviously there's hybrid solutions that we should be looking at as well. And then also the full life cycle from construction all the way through to design for disassembly and recycling. So looking at this graph, you can see that the operational carbon is kind of going along here in an upward trajectory. And we have a few steps in embodied carbon as well, where things such as windows may need to be replaced or other elements around the building. So we aren't just locking in one set amount of carbon, we're actually, we need to look at the retrofitting of the building as well. So the embodied carbon, I think, is one aspect, but the operational carbon also gets locked in at the upfront stages. So if we don't design a really energy efficient building, we may see this actually overtake the amount of carbon that was actually embodied in the building to begin with, and throw in some, odd and crazy climatic conditions, such as heat waves. We might actually see that line increase more rapidly as well. So all in all, we need to look at the upfront design of our buildings, but also the retrofit of our existing ones. So goal is to bring all of this down to zero. Now it's actually, there's a certain order that we should be following in this process to net zero. It's not as simple as offsetting to begin with, which unfortunately has become the trend. So offsetting should really be one of the last steps we actually take. We should be actually creating really efficient buildings with low embodied carbon, but really efficient operations. So that's where our passive, active and plant criteria come in. Then we should be adding in renewables just to top up that energy that we need. And then only then should we be offsetting. And then it gives us the opportunity to maybe even go beyond zero as well. And this is where the passive house standard really comes in. So if I flip back to that slide, sorry, this is the area that Passive House really does, you know, hit the nail on the head with. It can help us reduce our 28% of operational carbon. Now, it won't do everything. The Passive House standard doesn't cover things like water and biodiversity, but it does do energy and health really, really, really well. And I say health because that is one of the key components of the Passive House standard. There's no point having an energy efficient building if it isn't nice to be in and doesn't promote occupant health and well-being. So, quick overview. As I say, it's a health and comfort standard first and foremost, and then it's also an energy reduction standard as well. So the ultimate goal is to consume as little energy as possible whilst creating the most perfect spaces to be in, essentially. So the principles of Passive House are all built on good passive solar design. So that's orientation, cross ventilation, solar access in winter, shading in summer. Really, really simple, you know, site orientation, all of those things. Really simple, basic steps of sustainability. But then we're actually adding on some steps as well, because we're seeing that sites actually aren't always, you know, privy to the best orientation. They don't always have the best air quality outside of them. They might be next to a busy road. We can no longer rely on cross ventilation solely to provide nice spaces inside and good air quality. So this is where we add on these extra steps. So that's continuous insulation, mechanical heat recovery ventilation, thermal bridge mitigation, and airtightness. And we obviously need components to be able to do this as well. So high performance, airtight windows with thermal bridge mitigation in them. Now, the criteria of Passive House, this is where we get a bit more technical. We actually have to keep the heating and cooling demands below a certain point. So we're benchmarking here. We're benchmarking at 15 kilowatt hours per metre squared per annum. And that is the total heating and cooling demand that you're allowed. And you're not allowed to exceed it. Otherwise, well, you don't, well, if you were certifying a Passive House, you wouldn't quite get there, but it just at least levels the playing field. So we've got something to work towards and to check against. There's a cooling load allowance and a primary energy allowance as well. There's an air tightness target of 0.6 air changes. The average Australian home is about 10 to 15, so that gives you a good indication of how tight these buildings are. There's a frequency of overheating as well. So it says 10%, but really we should be aiming for 5%. And when I say overheating, I'm not talking about, you know, absolutely cooking people. I'm talking about over 25 degrees, which is still actually quite comfortable. And there's also some criteria around U values for windows as well. So as I say, it's a comfort standard. We're looking at indoor environmental quality, and we want to try and keep this internal band of temperatures steady throughout the year, even though the external temperatures may be fluctuating. So that's just an example of how this is a health standard as well. So what does it mean to go from code to Passive House? So I'm going to guide you through a case study that I presented at the Passive House conference. It's on multi-residential buildings, and I look at what NatHearse and the PHPP softwares can actually tell us and help us to achieve that net zero operational target. So the scope of this study was basically looking at the NCC minimum for residential buildings, which is 6 NatHearse stars, looking at industry best practice, which is 7.5, and then looking at what it would take to go to Passive House. And if there is a gap, what is it? So these are the types of buildings that we put into the study. We're looking at a GFA between 5,000 to 15,000 square metres, a mixed use program with residential at the top and retail on the ground, which is a fairly standard formula for multi-res buildings in Australia. So we looked at, firstly at a typical construction, which is concrete and steel. So don't worry, we will get to the timber, but I think this is important to flesh out because this is the standard construction methods in Australia at the moment. So unpacking the baseline, we modelled this building in NatHearse software First Rate 5, and we got these results, which is the annual heating demand. Again, this is kind of a good benchmark of the amount of energy that this building will use. In Melbourne, we're driven by heating demand because it's a heating dominant climate. So with the NatHer software, we actually got we got some pretty interesting results. We actually almost reached Passive House standard with 7.5 NatHer stars, which is pretty good, right? And we were quite surprised by this result. Now, if there's any passive houses on the line, this will also you will have gone through this process yourself, and yeah, just bear with me. So we also modeled the same buildings in the passive house planning software, and we got these results, which is quite interesting because they're a lot higher. So it looks like a lot more energy is being used to keep these buildings comfortable, but really it's the same building. So what's changed? Well, really it's the software we're using and the assumptions that are modeled. So what we're actually looking at here is incomparable. We can't compare these two results because they're not based on the same baseline. It's like comparing apples and oranges. So, for example, the PHPP will take into consideration thermal mass variations. It will take into consideration tongue twister, window quality. It will also take into consideration repeating stud thermal bridges in the walls, air tightness, and linear thermal bridges around the perimeter of the building. So what I'm going to do is I'm going to walk through each of the 5 principles of passive house and see what performance uplift we will get if we actually model them. So the base case, business as usual, as I say, we're using concrete, we're using non-thermally broken frames, steel studs, which are unthermally broken, approximately 10 air changes, and no consideration of thermal bridging around the perimeters. And these are the results that we're getting. So it's quite interesting that we're actually almost at passive house standard in the NatHer software. So first of all, I think the most important thing is just to optimize your base case without even going to passive house. Just good design here. Optimize your window to wall ratio, look at your window system performance, and look at your envelope performance. There's a good sliding scale that we can look at here, and these are types of tools that we work with architects with and to help guide the very beginnings of the design process. So your window system U value will affect your average window to wall ratio and where you can kind of how much window you can have versus what performance of window system you need. Likewise with the R value in the walls and the U values of the windows. So all of these things are interrelated and it's almost a parametric exercise, but there are some good rules of thumb that you can follow. So if you invest in a good glazing system, you can maximize GFA because your walls will get thinner. Simple. So what does this mean in terms of energy reduction? We modeled all of these steps of optimization in PHPP and we got these results. So just by going from NatHer 6 to 7.5 star, we shaved off 11% of our annual heating demand, and enhancing glazing systems, 17% was reduced and 21% was reduced when we enhanced our wall systems as well. And this is an accumulative study as well. So these are the values that we used for this particular assumption. So what happens if we mitigate thermal bridges? So thermal bridges, as I say, there are several types. There are repeating, which are within the wall system itself. So your steel studs are acting as mini thermal bridges all around your building. And you've also got perimeter thermal bridges. So as I say, the steel studs should be insulated in some way, shape or form with a layer of extra insulation or some sort of non-thermally conductive material, just to break any kind of transfer of heat and energy from, say, top hats to the steel stud and into your building. What else is really important about thermal bridging and mitigation is the risk of condensation that you get from this thermal bridge. So you're having hot air meeting a cold surface, and like a can of Coke, you get condensation. This is going to happen behind your plasterboard, and your plasterboard is a sponge where mold can grow. And you may not see it, but it's pretty much, yeah, it's a high risk if you have thermal bridges all around your building. A good way to mitigate it is actually to use timber because it's a less thermally conductive material. And remember, you can actually derate your whole wall system if you don't thermally if you don't thermally mitigate your stud system. So you can actually derate your wall by 43% if you don't do that. So the other type of thermal bridging is linear. So this is all the junctions around your building where your roof meets your walls, for example. So by mitigating these thermal bridges, we can actually shave off another 10% just by looking at the walls, and 26% if we look at all of those big, long thermal bridges around the perimeter. And in total, we're now improving on code by 46%. So what about mechanical heat recovery? Now, why is it important? Well, we want to prioritise natural ventilation first and foremost, but we want to also have this sort of supplementary system of a heat recovery mechanical ventilation system. This will allow us to bring fresh air into the building without actually losing any energy, or recovering 95% of it at least anyway. So this is a highly efficient process, and it's not like opening a window and letting all the cold air in winter. You're getting your fresh air without having to lose all your lovely warmth that you've just put into the building. So we have a winter mode, as I say, that recovers heat, and a summer mode with a bypass, which allows you to, kind of skip the heat recovery process because you don't want to be recovering heat that you're trying to get out of your building. So this will shave off another 10%. Seems like not a lot, but you know, this is an accumulative study, remember, so we're actually now improving on the performance by 56%. The other aspects, it's because it's not all about energy, it's about health. So in terms of internal air quality, we really need to be focusing on ventilation. This is a really big topic at the moment, as you all know, and respiratory health is pretty important. Now, a heat recovery system will also help you moderate and manage the amount of humidity and moisture in your air. If it goes below a certain amount, below 40, it can trigger things such as viral transfer in the air. If it goes over 60% as well, you get bacteria and mold growth. So we want to be within this 40 to 60% range of humidity at all times. And that's actually the easiest amount of humidity to breathe and helps our respiratory system. We can also integrate filters into our HRV system, which allows us to filter particulates out of the air before it even comes into the building. So again, if you live next to a train line or a busy road, you can start filtering out some of the really dangerous particulates in the air before they come in. And yeah, instead of having to open a window, you still get your fresh air. What other things are really important about the mechanical ventilation system is, as I say, it filters the air. So in a really smoky bushfire season, we can actually maintain really, really good air quality inside. And this was proven with the Torrens Childcare Centre. This project was presented at the Passive House conference, and they actually used it as a refuge during the fires in Canberra earlier this year. And that's a picture of the owner's daughter, you know, happy as Larry inside, whilst it looked very soupy outside. So airtightness, the next one. We're looking at the windows and doors. Basically, the whole envelope needs to be airtight. So that includes windows and doors, and it includes all of the wall systems, any junctions around the perimeter of the building. We also want to include a vapor control barrier here as well that allows vapor to wick out of the wall rather than getting trapped in. So it's not like wrapping your house in a plastic bag. It's almost like wearing a Gore-Tex rain jacket, which allows your building to breathe a bit. So it seems a bit contradictory. It's airtight but vapor permeable, and they're called intelligent membranes for a reason. So this is sort of a very rough cross-section of what that wall would look like. You'd have your vapor control on the outside, in the Melbourne climate that is, and the air barrier on the inside. And there's lots of different tapes, membranes, and ways that you can achieve this, and often materials themselves are quite airtight, like CLT to a certain thickness, and also concrete. But if you're using a lightweight system, you might be using a sort of building wrap on the inside. So this will shave off another 23% of your energy if you just install airtightness. Again, all of these things are an accumulative study. So on their own, you might get a slightly different result. And this is assuming it's going from a 10 air change rate down to 0.6 at 50 pascals per hour, which is almost like a strong wind blowing against the building. So all in all, we've reduced our energy demand from our code building down 80%, which is pretty phenomenal. So that will make actually recovering that extra 20% with renewables much, much more easy. So airtightness and the broader benefits, I think, again, this isn't just about energy reduction, this is about human health. It actually helps us to, when in combination with the thermal insulation, will help us control acoustics. So if you would, you know, in this scenario, you won't hear that train whizzing past you. It helps us to control the indoor environment by separating it from the external one. So you're not just getting a bunch of dust or smoke seeping into your building through all the cracks. It helps us control drafts and therefore thermal comfort. We're not losing any energy basically through the envelope itself, and we can just control it with our other systems. So at the end of the day, the cheapest energy is the energy that you don't use. So all of these things are really, really important to consider. So where does timber fit in with this? Well, as I say, avoiding locking in carbon up front is really important. And I've just been talking about operational side here. We really do need to look at the embodied side as well. So this is, I guess, we all know timber is a fantastic material to use. So we did the study on a few different systems as well, integrating timber in different formats. So looking at CLT with a steel stud facade system, again, quite a common sort of hybrid system that is emerging in the industry. We're looking at concrete with a lightweight timber facade system, a CLT, fully CLT system, and a CLT with a lightweight timber facade system. So lots of different combinations here. And yeah, the results are quite telling. So in the grey, you've got the business as usual, steel and concrete. In the green, you've got steel stud with a CLT slab system. So those two are very similar. And I can only say that it's because of the steel stud system around the facade not being thermally mitigated. Now remember, we're using a sort of business as usual construction model here. We're not kind of optimizing this system at all. We're just plugging it straight into PHPP and comparing the base case. So yes, it's quite telling that these steps are kind of hindered by using a steel stud system if it's not thermally broken. Now in the blue, you've got your concrete and lightweight timber system. So again, assuming that the lightweight system goes around the edge of the concrete slabs and you don't have any thermal bridging, you actually can shave off quite a lot of energy up front, and the same with the two fully timber systems. So I think as a summary, it's really quite amazing how much energy we can save just by using timber in different ways. And obviously that alone, just using timber alone, will not get us to net zero. We need to start integrating these next steps. We need to start looking at enhancing our glazing, our wall systems, reducing our thermal bridging. We need to mitigate essentially all our linear thermal bridges. We need to look at a ventilation system with heat recovery, and we can do all of those things, but we still don't quite get to passive house. It's the airtightness that will get us there. And that's what I guess the passive house standard is probably best known for, its rigorous airtightness. And that's why you just won't meet that 15 kilowatt hours per metre square per annum if you don't build it to 0.6 air changes. So yeah, just a bit of a summary, and you'll get these slides at the end of the presentation so you can go back and pick through it. Now we also obviously plug this, we want to compare this to what we got in the NatHERS software as well. So same building, same assumptions, this is the result. Again, the bar in the pink is the compliance software, and the grey, green and blue is the PHPP analysis. And again, I think there just doesn't seem to be a correlation between these results. Yeah, there's just, it seems like too big a step down, and there's not really much, I guess, evidence of how that is happening. So as built performance, is one thing on paper, but it should be verified. And I guess the reason why the passive house standard is so, I guess, widely used around the world is because the verification process allows you to check whether the building has actually been built to that standard. And it's that final straw, it's that final thing that you can basically give to your client and say, you got what you paid for. Because they might be paying for this and you might be paying for this if it's your building, your client, etc. But you might actually be getting something like this because the as-built performance just doesn't consider some of the really, really fundamental things of good, sustainable, resilient and healthy design. So passive house and timber construction, international and local examples. So the UK has actually done a lot in the space of timber passive house design. This is a school by Archetype, architecture firm, and this is their 3rd generation passive house school. And I call it a generation because they've actually designed and constructed multiple versions of passive house schools, and each time have learnt from their previous I'd say, mistakes and successes, and they've integrated it into their next project in this a constant feedback loop. They've used a lot of mass timber in their constructions as well, because it does offer the opportunity to manufacture components off-site, and so they come together and fit together like a glove. So looking at some of the results from these schools, as you can see in this graph, the yellow was one of their non-passive house schools, and they're looking at air quality in winter in the classrooms where I guess the teachers weren't opening windows for fresh air and relying on their recirculating heating system, and their parts per million of CO2 were spiking to sort of the 5,000 range, which is actually quite dangerous. And there is no way that kids will learn effectively in that environment. You'd be falling asleep at your desk. So looking at their next generations of schools, they're pre-passive house, so I guess it was a passive house design but wasn't certified. They got down to, you know, the 2,500 mark. And then their next iteration, they got down to a much more acceptable 1,500, and then again their second generation was even better. So I think this just is really telling that that quality assurance process is super important, because you need a benchmark to compare your performance against, and the results sort of speak for themselves. So you all know this building. I was fortunate enough to work on this up to tender on the architectural team. And this utilised mass timber construction. And this was part of Monash's, I guess it's their poster child now for the zero carbon campus, but they want to achieve zero carbon by 2030. And this was their project, which was going to sort of really lead the way in that. So not only does it utilise, you know, carbon sequestering materials like timber, but it's also fully passive house certified. And 150 bed student residence with teaching and community spaces on the lower grounds. So we used, as I say, a mass timber construction system in this building. It allowed us to design to super low tolerances, so there was less guesswork on site. And as I say, that airtightness is hard to achieve. So accuracy is your best friend, and you know, the shop drawings for the CLT and everything were absolutely millimetre perfect to how the windows would fit in. And I think this actually was a saving grace on site, because everything kind of came together, it fitted together like a jigsaw, and all they had to do was tape the junctions. They also used pod systems for the bathrooms and other sort of time-saving aspects as well. So lots of prefab elements came together in this really, I guess, efficient to construct building. I'd like to mention also that the program for this building, we shifted a lot of the design effort to the forefront. It wasn't a traditional D&C contract. We utilised early contractor involvement contract here to help us as the architects to understand how it was going to be built and really ensure that the quality was going to be achieved on site. So Multiplex, the builder, came along and we basically workshopped through all of the potential risks of achieving the airtightness, of you know, mitigating the thermal bridges, and essentially just keeping the costs down as well. So a lot of design and I guess muscle went into this sort of early design stage so that the off-site manufacturing and on-site construction could be kept as lean as possible. So as I say, there's an inbuilt quality assurance and quality management process within the Passive House standard, which allows you to check these things. So looking to the rest of the world, I was fortunate enough to go on a study tour last year, visit Vancouver, New York and Brussels, and look at what they're doing in the space of zero carbon construction. And they're all using the Passive House standard as their benchmarking tool. So for example, the City of Vancouver is now incentivizing developers to hit the Passive House standard in order for them to achieve their 2030 net zero goal across the city. And they've seen an uptake of 20% of all buildings just going, yep, we'll do Passive House. Obviously, there's a lot of mechanisms behind this that need to be in place. But essentially, if the government kind of understands where it needs to go and the industry can show it how to get there, I think together we can achieve some amazing things. So for example, the government understands that, you know, this is a risk to developers in a way. This is a new thing. This is a new process. There is an amount of onerousness on the airtightness, for example. So how can we make this more appealing? So they're actually offering additional floor area, so 5% increase in GFA. They're also incentivizing them by allowing them different types of setbacks and a few relaxations around that as well, and rezoning. So this is a huge indirect, basically cash bonus for developers. And yeah, it's really pulled the whole supply chain up with them as well, because now they need windows, they need doors, they need better insulation, they need to get the membranes. The whole industry in their local area of BC has come to the table, and they're just seeing some amazing projects unfold after this announcement. So these are just some of them. So this is the Earth Tower by Perkins and Wills. That is a fully timber construction, and it's also Passive House. And we've also seen a huge increase in prefab construction companies come to the table with different pre-certified systems so that it makes it easier to deliver these buildings. So obviously BC is a big timber, has a long history in timber construction, so this just really went hand in hand for them. So to finish off with, zero carbon buildings, you know, are really, really important to achieve our climate goals. We need to look at holistic sustainability. So we need to look at operational carbon, embodied carbon, as well as health and well-being. So that's where the resiliency piece comes in, and our buildings can cope with whatever is thrown at them by the climate change issue. We also need to remember to include renewable energy. We need to consider water and water saving and integrated water cycle design. We need to look at sustainable transport, waste management, ecology and biodiversity, and obviously much more. This is not a one solution fits all. This is Passive House basically is part of the puzzle, and I think it does the energy and well-being and resilience as a foundation really, really well. And I think from that can be built on to with all of these other amazing sustainability initiatives. So thank you very much.
So please, those online, start posting some questions up there for Kate. This is a great opportunity to get them answered, and some amazing information sort of provided there. We've got some questions here. We'll just work through, but I've definitely got some questions for you as well. One from Luke here. How does the operational carbon saving from eliminating thermal bridges compare to the embodied carbon from added insulation material?
That's a really good question, and probably one for another set of analysis. It's something that comes up a lot, actually, and I guess I see a question about straw bale as well in there. Maybe there's other insulation products that we should be looking at. I know there's a lot of sort of recycled glass products as well. So maybe if we're looking at the embodied carbon of insulation products, yeah, we look at the recycled content within them and the processes that they use to manufacture these particular materials. I'm sure if we speak to our insulation suppliers, they'll have lots of information on this. I think everyone's kind of sort of getting a bit cluey about the demand for that information increasing. So yeah, it's a great question. I don't have the answer to it, but yeah.
So just sort of following on, you noticed the straw bale question then. Is straw bale with a mud render a lower embodied carbon option than a vapor permeable membrane, a barrier for lower embodied energy?
Well, again, maybe we need to look, you know, at where the boundary of our analysis is. Where's the straw bale coming from? Maybe the transport will, you know, supersede the, you know, the membrane. Who knows? But I would say by just looking at it, you know, straw seems to be a good, it's a byproduct material. I have heard a really interesting analysis on straw bale though, where the twine that they tie the straw bales together with actually has more embodied carbon than the straw itself, because it is a waste product at the end of the day. So it's quite interesting when you dive into these things, what the life cycle carbon analysis will tell us. Again, I don't have the numbers on hand about how much embodied carbon goes into the membranes, but it would be a really, really interesting study. So yeah.
There's a question here just asking about advice where there's a good place to get design information on CPH in warm, humid and hot, humid climates. Much of the Australian literature seems to focus on hot, dry or warm, cool, temperate climates.
That's also a great question. The Passive House Association has a lot of links to research in this area. I know that Marcus Strang has been doing a study up in Queensland on, I believe it's CLT and timber construction and passive house, and how those systems work in those really humid conditions, and often, you know, results in flipping the system completely with the air barrier on the outside, and all basically the same principles but in a different order. So it would be worth contacting the Marcus Strang. And there's I think there's a lot of universities up there looking into this as a research topic as well. So I'd say if there isn't any published literature out there at the moment, there's definitely research happening, and hopefully that will come online soon.
Yep. A question for Sebastian. How does changing the order of the modifications affect the partial outcomes?
That's a really good one as well. We picked a certain, I guess, pathway. We looked at thermal bridges first, and then ventilation, and then air tightness. Now, if you flip those and looked at air tightness first, you might actually get a different result. Yeah, again, I'd love to run this analysis in all these different ways. And yeah, maybe that's something that we can put into a paper or something to tell you what the best first step is, rather than what the I guess the most on paper logical step is, because I think that cost will come into this as well. So you know, maybe it's cheaper to use better quality windows than to go full, you know, airtight. I guess, yeah, the cost conversation needs to happen in parallel, because not all projects can, I guess, not all projects have the budget to go the full mile. Having said that, if you integrate these things up front and you have a designer and a team that really understands this, this type of building and this method, you will find ways to eliminate costs in other areas to allow you to achieve this. So again, the earlier you get your team on board, the more cost savings you will have at the end. If you take a standard building that's already pre-designed and try and make it passive house, that's where you're going to be hemorrhaging money.
It's a good point you made, Kate, just a second ago about that balance between, where do you go, air tightness or window quality. I mean, it's interesting, obviously in 2022, we're going to go to 7-star. And to be honest with you, talking to volume builders recently, not a lot of them have looked at what 7-star is going to mean. Particularly, it'll be particularly important in the cooler climates like Melbourne and Hobart and those, maybe less so in Sydney and Brisbane and those places. But they're not really sure. They haven't looked at the dynamics of that yet. And obviously, as we take our residential homes, which are pretty poor at the moment, and obviously in terms of air tightness, it's not a big thing we look at in Australia, whereas they do overseas. If we tighten up the air tightness, that might, as you said before, give you condensation problems. I mean, you need to actually have that air exchange unit in there to get rid of that CO2. But clearly this sort of step to 7-star is going to be that transition from single glazed windows to double glazed windows, which should have happened 10 years ago, really, in Melbourne. What's your thoughts on that, particularly in that residential sector? What do we need to be doing there to get better window quality? It's just ridiculous, a single pane glass window is like a big hole in the wall, yet we still accept it.
Yes, it is a bit worrying because it's not only an energy problem, but it's a condensation problem. I don't think you'd find any single glazed building in Melbourne anyway that doesn't just become a waterfall in winter. That's a huge health problem. As we go to 7-star, I mean, if you look at the Green Star Homes standard, now they're looking at sort of benchmarking 7 and maybe 7.5 star and introducing that as a sort of volume builder standard. And I guess at the Passive House Association, we've been collaborating with them and helping them build this standard up a little bit as well. But as you say, that the ventilation method is really important as well. So if you introduce any kind of air tightness, or even as our construction materials get better and our systems get better, our windows get more airtight, for example, our building quality gets more accurate with these prefab systems that are coming onto the market. I think we really need to look at accidental air tightness as well, even if it isn't prescribed, because as you say, this is our buildings were traditionally meant to be quite breezy and leaky, so that it would control the moisture build-up inside our homes. And yeah, as you get more airtight, that becomes a big issue. So I think, looking at a ventilation system, I would say it should have heat recovery in the cooler climates of Australia. Up in Brisbane, maybe not. Maybe it would have a humidity control in there instead, for example. I think that is probably one of the most fundamental things that we should change first before we go down the air tightness path. Obviously, single glazing is just ridiculous. It should have been outlawed a long time ago. But the more that we demand full quality systems, and I guess just pushing our suppliers to that next level, I think the demand will drive it. Unfortunately, we're sort of waiting for code, but I think there's a lot of volume builders and a lot of just builders in general that are really cluey about this and kind of pushing past standard practice as is. So it's not a blanket statement about all buildings, but yeah, if code could change as quickly as we need it, that would be better.
Two questions here, which are sort of similar. I'll give you both of them, but they're based, follow on what you're just saying then. One from Thomas who's saying, do you have any data on the inherent value to developers that passive design offers in terms of assessed value and attracting higher rental incomes per month? That sort of incentive about why people would do it.
That's a really good question as well. And I think because we don't have the volume of passive house buildings here yet, that data is harder to come by. It might be good to look towards Canada, towards Europe, towards UK. The UK have actually done a lot of studies around this, especially for social housing, where, for example, in the city of Exeter, they have basically just adopted the passive house standard as their minimum social housing standard. And they've done a lot of post-occupancy surveys and data collection on the performance of those homes. And yeah, their tenant turnover is much lower, health and well-being, so the pressure on the health system has been reduced because those people no longer have, you know, chronic asthma. Yeah, it's pretty phenomenal what I guess outcomes have been seen from just going down this path. In Australia, we've not really got many passive house projects that have been sold, so they're mainly ones where the owner has been, you know, really passionate and driven and has gone down this path. So they're like the front runners. There is one building in Sydney, the Fern, which was sold recently, and it's a multi-residential building. I believe you can still go and stay there. It's sort of a serviced apartment setup. So that would be quite interesting if they are conducting any post-occupancy surveys there, because although people aren't staying for long periods of time, a larger volume of I guess occupants are going through there, and whether the occupants realise any difference. I've stayed there personally, and it's in Redfern, near a train line, near a busy road. You know, it's a busy area, and it's like a little cocoon. You walk in and you just can't hear a thing, and it's just blissful after being, you know, on a you know, noisy train platform, etc. You know, comfort-wise as well was really lovely, but I think the experience of these spaces alone should increase the value of them. I mean, you don't know what you don't know until you experience these sort of soft qualities that aren't necessarily measured. Yeah, I think that will be the big selling ticket. But we just don't have the sort of volume of buildings to for people to stay in, for people to experience. So in Canada, they most of the construction companies that went down this path had a display suite or a display home that they just let people go and stay in. So that was how they marketed this new building standard, through experience.
Yep. A question here, just how different would the thermal bridging be in warmer climates like the Gold Coast, where heating and cooling loads are almost the same?
Yeah, again, it would be good to do a bit of further analysis on this, and I'm sure, as I mentioned, Marcus Strang has done a lot of research on this through his PhD. I imagine thermal bridging isn't as important in those climates, but on the other hand, you're probably, if you've got any kind of sun hitting a steel beam that's coming into the building, you might be getting heat transfer into your building that you don't want either. So it might not be necessarily the condensation issue, but it will be other issues. So in general, I think they're just, you know, just a bad idea, but the severity and the impact of them will probably vary.
Mm-hmm. Question here from Sean: is the 15 kilowatt per hour per metre squared a heating cooling criterion constant no matter no matter the building, or does it depend on how green the electricity generation is?
That is no matter what building, no matter what size, no matter what occupancy use, all of those things. It's just a benchmark. The primary energy and primary energy renewables is the one that will factor in the source of your grid energy and how green that is. So there's a sort of it's very German, so I'm not even going to attempt to sort of unpick that for you here, but there's a kind of a calibration, and it takes some assumptions from the grid. And over in Germany, they have these big district heating plants and big renewable big renewable power systems, etc., which we have here as well. We can purchase green power, so I think that would definitely impact that score, but not the heating demand.
Yep. And a question, have you recorded the mean radiant temperature or the operative temperature of a room under passive house standard conditions?
There was actually a really great video that Chris Nunn, the sustainability manager of AMP, is building his own passive house up in Asquith in Sydney, and they've just sealed it all up, put the windows in, and I believe it was on LinkedIn that he posted a video of how hot it was outside and what the temperature was inside, even without, you know, the ventilation system or anything, just by sort of hyper insulating and sealing the building envelope. And don't quote me, but I'm pretty sure it's 37 degrees outside and 26 inside. So I feel like that kind of speaks for itself.
There's just sort of two questions here, which I think are a nice sort of interlink. One from David saying, to what extent, if any, does the passive house discipline constrain creative design in the context of client budgets? And actually, interestingly, in the thought someone else has pointed out, the Victorian government's recently announced social housing program. Is this a golden opportunity to push passive house forward?
100%. I think, look, if you're armed with the knowledge from the beginning, you can find ways to navigate this cost issue. It shouldn't cost more. These buildings shouldn't cost more, and in many parts of the world they don't. They're on par with you know, standard buildings. Obviously, it depends what you're comparing. At the moment, we're comparing, you know, 6 NatHo stars, which is, you know, down here, with something up here. So the cost difference probably will be quite substantial. But again, that cost difference is normally calculated on the same building, the same base design, just having passive house sort of, you know, plastered onto it as a retrospective idea. If you consider these things up front, you consider, you know, where to put the windows, where, you know, the optimal window to wall ratio, the optimal, you know, surface to volume ratio is. So the more compact the building is, the more, you know, the less insulation you'll need, the less envelope you essentially have to deal with. So these things all really, really impact cost. So if you've got the right team, you've got the right consultants on board that can give you this advice from the beginning, I think that's where the cost savings will come out. But unfortunately, buildings are often, they're all special snowflakes. They're all slightly different. They're in a different council. They're in a different on a different site, and you can't always compare them apples for apples. The social housing is a really fantastic opportunity to do that, because they'll want standardization and they'll want to be able to roll these out at least as a standard envelope specification. You know, again, I think councils also need to come on board, because they will have their own neighborhood character requirements that will, you know, basically dictate the envelope of your building and the massing of your building. So I think there's a conversation to have with local government and policymakers in this as well, to really make this a more cost-effective option for people, because at the moment we have to sort of pander to them and also try and, you know, tick all these other boxes, and often we're not given the best springboard to begin with.
That's a really interesting point you make. In the interviews we've done recently through FWPA with volume builders, we were asking them on a range of questions around environmental friendly materials. Would, you know, customers pay for them? Generally, the answer was no. They'd rather put their money into stone bench tops, and another sort of point for their high definition telly, even though the companies, the building companies, want to be seen as good corporate citizens. But even the question around energy efficiency, you know, do people value the sort of higher levels of energy efficiency? Why aren't they using double glazing? And then the builders again sort of said, you know, people in that purchase point just aren't prepared to put the money into double glazing. They want the stone bench top. And really, you know, some of the volume builders can't understand this at the moment, particularly with energy prices going through the roof. You know, the payback on those now is much quicker. It's interesting how we're going to change those attitudes with consumers about, you know, valuing these sort of things you're talking about today.
I think it's just an education piece, and letting them know what the long-term costs of not putting these things in is as well. So again, it's all a bit of, you know, we need to do a desktop study to say, look, this is what your energy costs will be if you don't put double glazing in. You know, I think that in itself will kind of frighten people into wanting to have them, at least. Laying out the health impacts of it, but also I guess getting banks on board with, you know, allowing them, you know, flexibility in their borrowing capacity for these types of things. So the Bank of Australia has a green mortgage scheme. So it gives you a discount if you're going for, I think it's 7.5 stars or something or above. And I think as soon as banks start to recognize the quality and basically the impact on people defaulting on their mortgages because of, say, high energy costs. I think it's a risk mitigation strategy at the end of the day. And I think the Insurance Council of Australia is also cluing on to that as well. And so hopefully we'll see insurance rates also drop with the increase of quality of our buildings, because it's all about resilience.
That's been fantastic, Kate. We're just on 12 now, so we'll wind it up. So on behalf of everyone online, I really thank you for an excellent presentation, very professionally presented, and some great data involved with all that. I'd encourage people, if they want to go back to re-look at the details there, because there's lots of great information in there. So a bit of a virtual clap to you. Thanks, Kate, and
Thank you.
thanks once again for participating. Just a reminder to those people online about next Tuesday's webinar. It'll be on mass timber and VDC technologies, so keys to creating more efficient and successful projects. So we look forward to catching up with you all again next week. Also remind you about the mid-rise webinars on Thursday if you're interested in that. So thanks once again. We'll see you another event.